Okay, hi guys. So in this lecture, we'll be discussing about the application of resonance and hyperconjugation and inductive effects. So let me write down the heading first. So the applications of resonance, hyperconjugation, and inductive effect, or other effects. Okay. So we'll be discussing about these things: bond energy, then heat of hydrogenation and heat of combustion in the upcoming lectures. Then we'll be talking about aromaticity, then stability of intermediate, and finally acid base. So how these concepts are going to be affected by the concepts of resonance, hyperconjugation, and inductive effect, which can be seen in different compounds. So we'll be seeing the application of these three effects in these broad areas. Okay, so first let us get started with bond energy. So bond energy is always compared by making free radicals in gaseous form. Okay, so you can just write that on discussing the bond energy between two atoms in a compound, so it is always compared by making free radicals of atoms in gaseous phase or gaseous form. Okay, so we can say that bond energy of the existing bond between two atoms is actually inversely proportional to the stability of free radical after making those free radicals in gaseous form. Stability of free radicals. Okay, so whenever you have a question coming of the sort that you have to compare bond energy of a given between a bond energy of a bond between two given atoms, then you have to first convert those atoms into free radicals, and you have to check, you have to see that if the free radicals are more stable, then obviously the bond energy would be lesser. Okay, so you can write in other words as more stable radical in gaseous phase, more stable the radical in gaseous phase, less will be the chance of bond formation with another free radical, because the compound is already very stable in itself, that after the formation of free radical that it will not combine with any other free radicals. Okay, less will be the chances of bond formation with another free radical. Okay, so let's say for an example we are seeing this we have to compare the bond energy of this C atom and this H atom. So what we'll do is we'll break that atom into free radical form into something like this and H dot, and as you know that and we have to compare the bond energy of this compound with this compound. Let me again write it, CH. Okay, so we have to compare the bond energy between of C and H in this compound and in this compound. So we will compare the stability of free radical of these two carbon compounds or free radicals when we actually break them into free radicals. So obviously, as you can see, that it is a case of Hopper conjugation between a free radical and a double bond, which we have already seen so many of these cases, which is actually stabilizing this compound. Okay, so more stable product, less is the product's bond energy. Okay, so as you can see that the inverse proportional between the bond energy and stability of free radical, so it is more stable, hence second one has less, or you can say that this compound has lesser bond energy. Okay, and as less is the chance and more the stable free radical, less is the chance of again collision with H plus H dot free radical. So again I can write it as more stable product. By product I mean more stable free radical. This implies less is the chance of again colliding with H dot free radical. Okay, so I'll give you two such examples or two such free radicals which are highly unstable. One of it is this, on a free radical on a benzene ring and a free radical on alkene. Benzene free radical and alkene free radical, we call them as, this is aryl, formation of aryl radical, and this is formation of vinyl radical. So if these two are formed in any reaction, then these are highly unstable. Please remember this. As a matter of fact, this question is asked so many times in JEE level competitive examinations. The combinations of such questions are repeatedly and regularly asked in every year's paper. So please remember that these two are highly unstable free radicals. Wherever you see them, just remember that those are highly unstable, and it's better that you don't ever encounter these two as a part of any reactions. Okay, whenever you have something like these two as an intermediate, the reaction will immediately go in the backward direction. It will not proceed in the forward direction. Okay, let's see some more examples in which we have to compare the bond energy of C and H bonds in these compounds. Okay, so we have something like this. And why are they actually unstable? You can see that the double bond is actually having sp2 character, hence and it is more electronegative, and on the top of it, it is also acquiring a free radical on electronegative element, so which is obviously going to be more unstable. So you have to compare the bond energy between C carbon atom and H1, H2 and H3 hydrogen atoms. Don't worry, they are the same hydrogen atom. Just for the understanding sake, I have given them the suffixes. So what would be the bond energy? Obviously H1 would be higher than H2, H3, then it would be higher than H2. Why? Because H2 can be easily involved in free radical and double bond conjugation when we remove H2 and have a free radical over here. So it would be something like this. When H2 is removed, we would have something like this structure. So H2 would be actually involved in resonance with this pi bond. Okay, hence H2 is the least stable because its free radical in gaseous form is more stable. Hence, more stable the free radical, less is the bond energy. Okay, and in H1 and H3, obviously H1 is having in gaseous form free radical on a double bond, the formation of vinyl free radical. Hence, it would be having the most bond energy because it is highly unstable among H1, and H3 would be someone in between H1 and H2. Okay, I hope you can guess the reason why. Okay, let's do for this example. We have this is H2 and this is H1, so you have to compare the bond energy of H1 and H2. So in free radical, if we make by removing H1, we would have free radical like this, CH3 would be here, and if we remove the free radical at position number this, we would have something like this. So obviously this is more stable. Why? Because of 6 alpha hydrogen, and in this case it is less stable because it is having only how many? 2 alpha hydrogens. So obviously this is more stable, hence its bond energy would be lesser. Hence H1 bond energy should be lesser than H2 bond energy. Okay, let's look at this example. We have H1 here, H2 here, and H3 here. H3 would be the least stable. Why? Because of the formation of aryl free radical. Aryl free radical is highly unstable, hence its bond energy would be the highest, not the lowest. Its bond energy would be the highest. It is very, very difficult to break this bond because in free radical, aryl free radical is formed. Hence H3 would be the highest bond energy. And what about H2 and H1? So if we draw the free radical when we actually break the H1, so we would have free radical here, and on H2 if we form the free radical, we would have something like this. So in this case, as you can see, the double bond is in conjugation with the free radical, so it will support it, and hence H1's bond energy would be lesser than H2's bond energy. Okay, so let's look at another example. CS3 okay, so this is the compound, and if we have to compare between H1, H2, H3, H4, H5 and H6. Okay, so what would be the order? So as you can see, on H2 is attached directly to the double bonded carbon atom, hence H2 would be the H2's bond energy would be the highest. Then obviously, as you can see, that H3 is actually involved in resonance with the carbon which contains H3 on having a free radical would be involved in resonance with the neighboring pi bond, hence H3's bond energy would be the least. Now we have to compare for H6, H4, H5 and H1. Okay, so for H1 you can see we have 1 alpha hydrogen. Oh no, but for H1 also, between H3 and H1 we have to compare, right? Because in both H3 and H1 we have a conjugation with a double bond, hence on H3, as you can see, there is a presence of actually 1, 2 and 3, 3 alpha on H3 and only 1 alpha on H1. Okay, hence H3 would be more stable than H1, hence the bond energy of H1 would be more than H3, because H3 is free radical, because the carbon on H3 will have 3 alpha hydrogen when it gets converted into free radical, hence it would be more stable. Hence due to the inverse proportion, Inversely proportional bond energy, H3 would be less stable than H1. Then H1 is done, H3 is done, H2 is done. Now only things left are H4, H5 and H6. So we have to compare them only on the basis of hyperconjugation, because resonance they are not even involved. So when free radical on carbon atom containing H4 takes place, we have 1, 2 alpha hydrogen here. On H5 we will have 3, 4, 5, 6, 7 alpha hydrogen here. And for carbon containing carbon which is joined to H6 will have only 1 alpha hydrogen. Hence H6 would be most having the highest bond energy, then H4, then H5. H5 is having 7 alpha, H4 is having 2 alpha, and H6 is having only 1 alpha. Hence bond energy would be of the decreasing order. Okay, let's have another example wherein we have something like this. H1 on the same H2, then we can have something like H5. This is a, then we have, this is a substituent, methyl substituent. This is, let's say this is H6, this is H3, and this is H4. Okay, so let's compare the bond energy here. As you can see, on H6 there is, if a free radical forms, then it would be a formation of highly unstable aryl free radical. Hence H6 bond energy would be the highest. H6 is out of the picture. Then comes, actually we can see that for H1, H3 and H4, oh sorry, for H2, H3 and H4, they will be involved in conjugation with pi electrons on forming a free radical. So H3, H2 and H4 have to be, will be the last. The order is yet to be decided. But for this order only, for H3, as you can see, we will have 2 alpha hydrogen for H3. For H2 we will have 3, 4, 5, 6 alpha hydrogen for H2, and for H4 we will be having 1, 2 alpha hydrogen, or for H3 we will be having only 1 alpha hydrogen. Yes, one alpha hydrogen, and for H4 we will be having 2 alpha hydrogen. Okay, you can count them, 1 here and 1 here. Okay, so their ordering would be something like H3 would be the highest, then comes H4, then comes H2. So H3, then H4, then H2. Okay, 2 alpha hydrogen here and 6 alpha hydrogen here. Okay, so H4, H3 and H2 are done. Now comes H1 and H5, which have to be compared only on the basis of alpha hydrogen. So H1 actually contains how many alpha hydrogens? 1 alpha hydrogen only. And H5 will contain 3 here, 2 here and 2 here, 7 alpha hydrogen. So obviously the relative stability order of H5 would be greater than H1, hence the bond energy would be bond energy of H1 would be greater than H5. Okay, so let's discuss the last example for this video lecture, and possibly for comparing the bond energy order. So we have something like this. This is H2, CH, H4, H5, CH2 and H6, and obviously we have H3 and CH2 and H1 here. So you have to compare the bond energy of these C and H atoms. So I'll leave you this task as your homework, and you will have something like this bond energy order. So I hope you get to the correct solution. So I'll give you some hints also. For H3, as you can see, H3's bond energy would be the highest because in free radical state we would have a formation of aryl free radical. Hence H3's bond energy would be the highest. Next comes for H1 and H2. You can see that these two are actually involved in resonance. Hence these two would be lowest. And for comparing between H1 and H2, you just see the number of alpha hydrogens. So number of alpha hydrogens are more in case of H2, hence its bond energy would be lesser than H1. So H1, H2 and H1 are also done. Now comes H4, H5 and H6. You just have to compare on the basis of alpha hydrogen. H6 has the least number of alpha hydrogen, which is 1 alpha hydrogen. Okay, what about the alpha hydrogen of H4? H4 will be having how much? 2 here and 3 alpha hydrogen. And how many alpha hydrogen H5 has? 3 plus 2 plus 2, 7 alpha hydrogens. Hence this would be the order. Okay, so with this we come to an end of this lecture. In the next lectures we'll be seeing heat of hydrogenation and heat of combustion, and we'll be continuing on seeing some more applications of resonance, hyperconjugation and inductive effect in case of the previously mentioned concepts like bond energy, heat of hydrogenation, heat of combustion, aromaticity, stability of intermediate acid base. So we'll see all these things in the coming lecture. So with this, good luck and goodbye.